Find the term stainless steel, making reference to the percentage quantities of its two main constituents. Stainless steel is a steel alloy with a minimum of 10.5% chromium by mass. Chromium is the key element that gives stainless steel its resistance to corrosion, staining, and pitting. Other elements such as nickel, molybdenum, and carbon are also often added to improve the mechanical properties and corrosion resistance of stainless steel. The percentage ranges of the two main constituents of stainless steel are, for chromium, between 10.5% up to 30%, and for carbon, 0.15% to 1%. With reference to fatigue failure of components, A. Describe how material fatigue testing is carried out in the laboratory. B. Sketch the surface appearance of a fatigue fracture. C. Describe the three stages of the failure. D. List the methods available on board to limit the possibility of fatigue failure to a propeller shaft. A. Material fatigue testing in the lab. Laboratory fatigue testing simulates real-world cyclic loading to assess a material's resistance to fatigue failure. Common methods include A. Rotating beam test. A rotating cantilever beam experiences cyclic bending stresses as it spins. The number of cycles to failure at a specific stress level determines the fatigue strength. B. Axial fatigue test. A specimen is subjected to cyclic tension and compression loading to evaluate fatigue performance under these conditions. C. Push-pull test. A specimen is pulled in one direction and then pushed back in the opposite direction, mimicking cyclic axial stresses. D. 4-point bending test. A specimen is supported at 2 points and loaded at 2 other points, creating a constant bending moment to study fatigue behavior. These tests measure fatigue life, number of cycles to failure, at various stress levels, generating S to N curves that map stress versus number of cycles to failure. This data allows material selection, design optimization, and prediction of fatigue life in real applications. B. Sketch of fatigue fracture surface. YouTube reference. A fatigue fracture exhibits distinct features. 1. Initiation site. Often a surface defect like a scratch, corrosion pit, or inclusion acts as the starting point for micro cracks. 2. Beach marks. Concentric semicircular ridges around the initiation site represent progressive crack growth under each loading cycle. C. Final fracture zone. This area displays rougher fracture features due to rapid crack propagation leading to final failure. Sketch drawing. Imagine a circular area with concentric semicircular ridges around a central point. The ridges become larger and closer as they move away from the center. The edge shows a rougher fractured area. C. 3 stages of fatigue failure. 1. Crack initiation. Micro cracks form and propagate at microscopic levels from stress concentrations at defects or inhomogeneities within the material. 2. Crack propagation. The micro cracks gradually grow under repeated loading, creating beach marks on the fracture surface. The rate of crack growth depends on stress level, material properties, and environmental factors. 3. Final fracture. When the crack reaches a critical size, it can no longer withstand the applied stress and rapidly propagates across the remaining cross-section, leading to final failure. D. Mitigation methods for propeller shaft fatigue. On-board strategies to limit propeller shaft fatigue failure include 1. Preventative maintenance. Regularly inspecting the shaft for surface defects, cracks, and corrosion allows for early detection and repairs, preventing further crack growth. 2. Vibration control. Minimizing vibrations through shaft balancing, alignment adjustments, and dampening devices reduces dynamic loading and stress concentrations. 3. Propeller maintenance. Ensuring proper propeller balance and blade pitch minimizes uneven loading on the shaft. 4. Material selection. Using fatigue-resistant materials can improve the shaft's overall fatigue life. 5. Operational monitoring. Monitoring stress levels, vibrations, and shaft RPM during operation allows for adjustments to operating conditions and early detection of potential fatigue concerns. By implementing these mitigation strategies, the risk of failure in a propeller shaft due to fatigue can be significantly reduced, ensuring its continued reliable operation and preventing catastrophic consequences. With reference to the attachment of aluminium superstructures to a steel hull. A. Explain why it is not normal practice to join the two components using conventional welding techniques. B. State the particular problems associated with the aluminium superstructure where it is bonded to a steel hull. C. Outline the maintenance that should be carried out to ensure the continued structural integrity of the vessel. D. Sketch a typical transition joint that could be utilized to attach an aluminium superstructure to a steel hull. A. Conventional welding techniques are not normally used to join aluminium superstructures to steel hulls because of the different electrical properties of the two metals. Steel has a higher melting point than aluminium, so that when the two metals are welded together, the aluminium can melt before the steel, resulting in a weak joint. Additionally, steel is more prone to rust than aluminium, and the heat from welding can accelerate the corrosion process. B. The particular problems associated with an aluminium superstructure bonded to a steel hull include galvanic corrosion. This type of corrosion occurs when two dissimilar metals are in contact with each other in the presence of an electrolyte such as seawater. The electricity from the steel hull can flow to the aluminium superstructure, causing the aluminium to corrode. Stress corrosion cracking. This type of cracking can occur in aluminium alloys that are subjected to stress and a corrosive environment. The stress can come from the weight of the superstructure or from the waves and wind. Fatigue. Aluminium is more susceptible to fatigue than steel, so the superstructure is more likely to crack under repeated loading. C. The maintenance that should be carried out to ensure the continual structured integrity of the vessel includes regularly inspecting the joints between the superstructure and the hull for signs of corrosion or cracking, maintaining the protective coatings on both the steel and aluminium, monitoring the stress levels in the superstructure and taking steps to reduce them if necessary. D. Sketch of a typical transition joint. A. Describe the problems associated with two dissimilar metals in contact in the presence of seawater. B. Describe 3 different methods that may be used to reduce the problems described in A. Dissimilar metals in seawater, a recipe for corrosion trouble. A. Problems with dissimilar metals in seawater. When two dissimilar metals come into contact in the presence of seawater, a recipe for corrosion is brewed. Here's why. 1. Galvanic corrosion. The primary culprit is galvanic corrosion. Dissimilar metals have different electrochemical potentials, meaning they possess varying tendencies to give up electrons and corrode. The more active metal, lower potential, acts as the anode, readily losing electrons and dissolving into the seawater. The less active metal, with the higher potential, becomes the cathode, attracting these electrons and remaining protected. This sacrificial process rapidly corrodes the anode metal. 2. Increased corrosion rate. Seawater acts as an excellent electrolyte, facilitating the flow of electrons between the metals. This significantly accelerates the corrosion process compared to each metal exposed to seawater alone. 3. Localized corrosion. The corrosion often concentrates at the point of contact between the metals, creating deep pits and grooves. This localized attack can weaken the structure and compromise the integrity of the components. 4. Stress corrosion cracking. In some cases, the combined effect of stress and the corrosive environment can lead to stress corrosion cracking. This can cause sudden and catastrophic failures, especially in critical components like propellers or shafts. B. Reducing the problems of dissimilar metal contact. Fortunately, several methods can be employed to reduce or eliminate the problems associated with dissimilar metals in seawater. 1. Material selection. Choosing metals with similar electrochemical potentials minimizes the potential difference and so significantly reduces the driving force for galvanic corrosion. This can be achieved by using stainless steel alloys, copper-nickel alloys, or even plastic components in strategic location. 2. Cathodic protection. This method actively protects the more active metal by applying an external current that shifts its potential to become cathodic. Sacrificial anodes made of even more active metals or impressed current systems can be used to achieve this. 3. Electrical isolation. In some cases, it's possible to physically isolate the dissimilar metals from each other through non-conductive coatings or gaskets or washers. This prevents direct electrical contact and eliminates the pathway for galvanic currents to flow. 4. Protective coatings. Applying specialized coatings like epoxy resins, polyurethanes, or zinc primers can create a barrier between the metal and the seawater, further mitigating corrosion. However, regular inspection and reapplication may be necessary. By carefully considering these methods and choosing the appropriate approach for your specific application, you can effectively minimize the problems associated with dissimilar metals in seawater and ensure the longevity and integrity of the marine structure and equipment. Remember, corrosion is a constant threat in marine environments, and proactive measures are crucial for keeping vessels and components safe and operational. With reference to osmosis in glass reinforced plastic GRP hulls. A. Explain the process of osmosis and the method by which osmotic blisters occur in service. B. Describe a procedure for the local treatment of a single blister. A. How water diffuses through the gel coat. Water diffuses through the gel coat via a process called osmosis. Here are the steps involved in this process. 1. Concentration gradient. There is a higher concentration of salt molecules in the seawater surrounding the boat hull compared to the inside of the hull. This creates a concentration gradient. 2. Semi-permeable membrane. The gel coat acts as a semi-permeable membrane. This means that it allows water molecules to pass through, but it blocks the passage of salt molecules. 3. Diffusion. Water molecules move from the area of lower concentration, inside the hull, to the area of higher concentration, seawater, through the gel coat. This movement is driven by the natural tendency of systems to equalize concentrations. As water diffuses through the gel coat and into the laminate, it can cause the resin in the laminate to break down. This breakdown process releases gases which can create pockets or voids within the laminate. These pockets can eventually grow large enough to form blisters on the hull surface. B. A procedure for the local treatment of a single blister. 1. Pierce and drain the blister, taking safety precautions. 2. Sand back to clean laminate. 3. Wash, rinse and scrub clean. 4. After drying, clean with acetone. 5. Mix and apply epoxy resin and silica filler. 6. Sanding and fairing. 7. Paint to finish. Explain, with the aid of a sketch, the design and operation of a thermocouple. State one limitation of the thermocouple, stating how this is overcome in practice. A. Thermocouple design and operation. Imagine two dissimilar metals joined at one end, forming a junction. This is the heart of a thermocouple, a simple yet powerful tool for measuring temperature. Here's how it works. Look at the sketch. Hot junction. The two metals are joined at the tip, placed where you want to measure the temperature. This junction acts as the sensor. Dissimilar metals. Each metal has its unique voltage curve, representing its relationship between temperature and electrical potential. Temperature difference. When the hot junction experiences a temperature change, the voltage difference between the two metals at the junction also changes. Voltage measurement. The two metals then lead to a measuring device, which detects this tiny voltage change. Calibration and conversion. Using pre-programmed equations specific to the chosen metal pair, the device converts the voltage change into a temperature reading. The choice of metal pair determines the temperature range and sensitivity of the thermocouple. Thermocouples are relatively inexpensive and robust, making them widely used in various applications. Overcoming the limitations. Reference junction and compensation. Thermocouples have one key limitation. Their output depends not only on the hot junction temperature, but also on the temperature of the connection point where the two metals meet the measuring device, called the reference junction. Any fluctuations in the reference junction temperature can introduce errors in the measurement. To overcome this, practical thermocouples employ a reference junction compensation technique. Reference junction sensor. Another thermocouple to monitor temperature sensor is placed at the temperature correction. The measuring device factors in the reference junction temperature, effectively subtracting its influence from the hot junction voltage reading, resulting in an accurate temperature value. This compensation method allows thermocouples to deliver reliable temperature measurements regardless of fluctuations at the reference junction, making them versatile and dependable tools for various industrial, scientific and marine applications. Remember, thermocouple technology, despite its simplicity, relies on the precise relationship between temperature and voltage changes in dissimilar metals, choosing the right metal pair, employing proper reference junction compensation, and utilizing a calibration for accuracy are crucial aspects of effectively harnessing the power of thermocouples. Explain each of the following control terms. A. Settling time. B. Repeatability. C. Dead zone. D. Hysteresis. E. Proportional bandwidth. A. Settling time. Settling time refers to the time it takes for the output of a control system to reach and stay within a specified percentage, usually 2% or 5% of its final value after a step change in the input or a disturbance. It reflects the system's responsiveness and ability to stabilize around the desired operating point. A shorter settling time indicates faster response and better disturbance rejection. B. Repeatability. Repeatability refers to the consistency of a control system's output for repeated applications of the same input under identical conditions. A highly repeatable system produces essentially the same output every time it encounters the same input, demonstrating consistent and reliable behavior. Dead zone. The dead zone is a range of input values around the set point where the controller produces no output change. In other words, even if the input deviates slightly from the set point within the dead zone, the control system remains inactive. This can be intentional to avoid unnecessary actuator movements for minor fluctuations, but it can also lead to sluggish response and steady-state errors if the dead zone is too large. D. Hysteresis. Hysteresis is a phenomenon where the output of a control system depends not only on the current input value, but also on the history of the input. It creates a different response for increasing and decreasing input values around the set point, resulting in a staircase effect. This can be desirable in some applications for switching actions, e.g. a thermostat, but it can also cause oscillations and limit control accuracy. E. Proportional bandwidth, PB. Proportional bandwidth, PB, is a measure of the range of input values that will produce the full output range of a proportional controller. It is expressed as a percentage of the set point and is inversely proportional to the controller gain. A higher PB means a smaller gain, resulting in less sensitive but more stable control. Conversely, a lower PB indicates higher gain, leading to more responsive but potentially less stable behavior. The figure shows a tank filling with liquid at a variable rate and an output regulated manually by an operator controlling a value. Explain, with the aid of a control block diagram, the control process taking place that enables the operator to maintain a constant tank level, H, for varying rates of fluid flow input. Note, fluid flow in will always be less than the maximum flow out with the valve fully open. The image shows a tank with a variable flow input and an outlet valve manually controlled by an operator. The tank level is measured by a sight glass. The control process. 1. Measurement. The operator observes the tank level through the sight glass, visually measuring the current level, H. 2. Feedback signal. The observed level serves as the feedback signal for the operator. 3. Comparison. The operator compares the observed level, H, with the desired level, set point, which is usually indicated on the sight glass or known based on operational requirements. 4. Error calculation. The operator mentally calculates the difference, error, between the current level and the set point. 5. Control action. Based on the error, the operator adjusts the hand wheel of the valve, opening it more to increase inflow, positive error, or closing it partially to decrease inflow, negative error. 6. System response. The change in valve openings affects the inflow rate, causing the tank level to rise or fall. 7. Adjustment. The operator continuously monitors the level and adjusts the valve opening as needed to maintain the desired level. Additional notes. In this manual system, the operator acts as both the controller and the actuator, making adjustments based on their visual observation and judgment. The accuracy of level controls depends on the operator's skill, experience, and ability to react to changes quickly. This system is relatively simple and inexpensive, but it can be challenging to maintain precise level control, especially with varying flow rates. For more accurate and automated control, an electronic level controller and an actuated valve could be implemented. A. Identify components A, B, C, D, E, F, G, and H shown in the figure. B. Explain the difference between a strainer and a filter in a hydraulic circuit. A. Component identification. A. Pressure gauge. B. Hydraulic motor. C. Relief valve. D. Directional control valve. E. Filter. F. Reservoir. G. Pump. H. Strainer. B. Strainer versus filter in hydraulic circuits. While both strainers and filters remove contaminants from hydraulic fluid, they differ in their level of filtration and purpose. A strainer. Its function is to remove large particles like dirt, debris, and metal chips to protect pumps and other sensitive components from damage. Its micron rating typically has a larger micron rating of 500 to 200 microns, allowing smaller particles to pass through. Cleaning. Usually cleaned periodically by removing and emptying the collected debris. A filter. Its function, it removes finer particles and contaminants that could cause wear and tear on components. Its micron rating is a smaller micron rating, 10 to 25 microns, to capture smaller particles than strainers. Cleaning may be replaceable or cleanable, depending on the type. In essence, a strainer acts as the first line of defense against large debris, while a filter provides finer filtration for optimal system protection.